Hello, Math 150 students. We are looking at 5.1 antiderivatives and the definite integral today. And I have a function written here as a reminder of derivatives. So what we're going to be doing is doing antiderivatives. So we're going to do the inverse of differentiation, which is called antidifferentiation. And sometimes it's called the indefinite integral as well. So let me show you if you have a function and f of x is equal to k, where k is a constant, then remember the derivative of that is 0. You know that. Derivative of a constant is 0. If your f of x is x to the n, then the derivative is in x to the n minus 1. All right. If you have f of x is e to the x, the derivative is e to the x. And if f of x is ln of x, the derivative is 1 over x. So this is what we've learned so far in this class, and you have to rewrite, doing a lot of algebra before you can use those derivatives. Now, if the derivative is 2, we have to know what the function is. So what function, when we take the derivative, gives us 2? So we're going the opposite direction. And I'm going to give it away here. I know the derivative of 2x is 2. So the derivative of 2x is 2. And you can always check by taking the derivative. I'm going to start confusing this with my other class. My other class I do a similar worksheet, but they call these antiderivatives and the function. But we're saying here's the derivative. What's the original function? So the derivative of this is 2. So that must be, and I can check by saying, well, the derivative of that is 2. So that is our function. Well, let me tell you, that's not the only function whose derivative is 2. If I put 2x plus 1, the derivative is 2. If I put 2x plus 2, the derivative is 2. If I put 2x plus 3, the derivative is 2. So what we do is we say 2x plus c, where c is a constant. So we're going to always have this plus c because we always have to consider some constant that we take the derivative of that will give us that same derivative. All right, now let's look at this one, 3. The derivative of what function is 3? It is 3x and plus c. So I can check. You can always check by taking what you just guessed. Take the derivative of that, and you know that that's 3. Derivative of a constant is 0. So that is my check. All right, and I won't always check. What about 2x? Now notice that this was a 2, became 2x, 3 became a 3x. 2x, if you remember the derivative of x squared, gives you 2x. All right, and plus c. So if I take the derivative of x squared plus c, over here, this is my check. That gives me 2x plus 0, and that is the function whose derivative is 2x. All right, now notice that if you had a constant, you ended up with an x in your function. If you have an x here, you end up with an x squared. So I know that if I don't have a 2 here, I still have one higher power, because if I take the derivative of that, the 2 comes down and I get an x, but I need to get rid of the 2, and to get rid of the 2, I just put a half there. All right, you see that? So if I take the 2 in front and multiplies by 1/2, it gives me the 1 in front of there, and my function is 1/2 x squared plus c. Now we can look at a function whose derivative is 2x plus 3, and what we're really doing is called the antiderivative. I'm going to write that up here. It's called the antiderivative. Might as well use the right word. And the antiderivative of 2x plus 3, I could just reach up here and say, well, x squared, the derivative of that is 2x, plus the derivative of 3x, and then I have to always just put a plus c on there. All right, and you can always check by taking the derivative. What about 3x squared? Now look at the power of this one is 2. So I know this is going to be 1 more And that's it, right? So if I take the derivative of that, 3x squared will give me that plus c. And again, you can come over here and take the derivative of that, and that gives you 3x squared. All right, now what about 3x squared plus x plus 2? Well, 3x squared, the derivative is, or antiderivative is x cubed, plus, and then that x up here was 1/2 x squared, plus, and then the 2 was way at the top, 2x plus c. All right, and you can check, derivative is 3x squared plus x plus 2, and then the derivative of that is 0. All right. So this is an x squared. Now we're going up a power, so I know that this is going to be x cubed, and that'll give me 3x squared, but I need to get rid of the 3, so when I take the derivative, I just get x squared plus c. All right, what about this one? The derivative has to be a 4th power. Antiderivative, I need to be saying this correctly. Sorry if I've been saying derivative. The antiderivative of this has to be up a power, so that gives me 4x cubed, and to get rid of the 4, I get 1/4 x to the 4th plus c, and notice a pattern here. So 1/3 x to the 3rd plus c, 1/4 x to the 4th plus c. This one's going to be 1/5 x to the 5th plus c. And this x to the n, well, it's going to be x to the n plus 1. It's 1 more. And then it's 1 over that n plus 1, that same power. See the 5 here, 1/5. That power gets put in a denominator, plus c. Now, you have to make sure that n cannot equal, let's see, it gives me 0 if I let n equal -1. So n can't be -1. Warning. Any number on the planet but -1. All right, antiderivative of e to the x is itself plus c. If you take the derivative of that, you get e to the x. What about 1 over x? This, by the way, is x to the -1. And that is where you can't use this power rule. See, if your n is -1, you're in the ln situation, and we're going to use absolute value of x because that's kind of the law of the land. The reason why we have absolute value of x is so that these domains can be the same, and you can accept that, or you can ask me later why that has to be absolute value. We'll trust that it's true. And then if I'm taking the antiderivative of e to the x plus 1 over x, it's going to be e to the x, because the derivative of that, plus, and then the 1 over x is this ln, absolute value of x, plus c. All right, I'll be back for the other side.